I want to thank everyone for coming to the last session of the symposium. We have a lot of interesting talks left. First up, we have Carlos Sopuerta, who's going to be telling us all about inference, using simulation-based inference for massive natural binaries. Take it away.
Thank you very much. So today I'm going to tell you about what we are doing in Barcelona towards the development of machine learning methods, in particular SBI methods for LISA, and we have started with massive black hole binaries. So the motivation, of course, is the situation we expect with LISA data analysis, where we expect that the data stream will be dominated by signals of many different types. And one of the challenges is how to detect all these signals and do parameter estimation and characterize all the sources associated with them, right? So, okay, so this is a problem that it's called the global fit problem, where we want to fit all the models, including the model for the noise at the same time. And there is already a lot of developments. In particular, there are already 4 prototypes of the global fit using traditional sampling methods that we are working well, and we expect that they will give rise to global fit algorithms. And the motivation here is to provide some alternative techniques that may be also useful, and also we can have different global fits of different nature. Okay, another motivation is alerts. I mean, we need to, in the last hours before merger of massive black hole binaries, we expect to get more detailed information about the location of these sources, and we will have to do some fast inference to inform electromagnetic or other types of observatories to find counterparts of this. And I will tell you why also this is connected to what we are doing. Okay, so yeah, one of the why simulation-based inference, so the idea is behind this concept of amortized inference, where we are still also in a Bayesian waveform, Bayesian framework, and the idea is that if we is to train some networks that we can always use them to analyze new data without having to start from scratch every time, right? So that gives a different perspective as compared to the other traditional stochastic sampling methods. So another motivation is that these are, in principle, you can develop likelihood field methods. We know that likelihood estimation is one of the most expensive parts of the calculation data analysis. So this is another motivation to develop these methods. Okay, the idea basically is that is to implement one of the implementation of this amortized inference concept is what is called simulation-based inference. There are other things, but the idea here is that you must have a very good simulator. So you have some theta represents here physical parameters that can generate in a relatively fast way the models, and then from there you can estimate, also give you also posteriors. So, there are different approaches to simulation-based inference methods depending on which part of the Bayes theorem you want to substitute, let's say. So this is the Bayes theorem, which tells you that the posterior is equal to the priors times the likelihood divided by the evidence. So when you try to have a neural network model for the posterior, we call this neural posterior estimation, and we have already the example of Dingo that has been working very well for LIGO and for LBK, and now there are some developments towards LISA. Another alternative is to model what will be the ratio between the likelihood and the evidence. This is typically called neural ratio estimation. There is also some working software which is called Peregrine. And finally, this one that you substitute the likelihood by a neural network, which is called neural likelihood estimation. So the names are not very original. And this is the approach we are going to take. And this approach that we have adopted, and I will tell you some reasons to use this one. Well, all of them have advantages and disadvantages. So this is a bit of literature. So the first two are two examples of already simulation-based inference method that have been applied to ground-based detectors. And as you can see, the ones after the line are examples of works that have already been published and have been applied to this. As you can see, there are things are developing very fast and for different kinds of sources already. Galactic binaries, also for extreme isolation spirals, for massive black holes, so, you know, and even for gravitational wave background. So people is working in this actively. Okay, so neural likelihood estimation. So the idea is to, as I said, is to replace the likelihood by an estimator. That in this case is a sort of neural network where phi are the parameters of the network, basically, typically like weights and biases. Right? You are familiar with neural networks. So then the question is how you model a probability distribution using a neural network, because in principle it's not trivial, as the neural network has to preserve the properties of a probability distribution. Right? So one possibility that has been used and is used frequently is the concept of normalizing flows. So basically, the idea of normalizing flows is to you start from a very simple distribution that you know. In our case, it's a Gaussian distribution, right? And then what you do is you do a transformation in the random variable. So your original variable is x. So you do a transformation that depends on these parameters and on the parameters of the source. So and then this transformation, the probability distribution transformed in this well-known way, which preserves the properties of probability distribution, because you are transforming with the Jacobian, and then the measures are preserved. So the idea of normalizing flows is doing this transformation from a very simple distribution to the target distribution in small steps, right? So you start from the Gaussian and you are doing a small transformation until you get into the desired probability distribution. So this is basically, in the end, the change of variable is the composition of all these transformations. Okay, so there are different ways to do this, and one way is to use what is called masked autoregressive flows, which is a type of neural network architecture where these transformations can be implemented in a proper way. Essentially, these transformations, they consist in simple affine transformations. So basically, it's a scaling and a shift. And in this way, when you apply the rules of the transformation, what you find is that your probability distribution is all this combination of probability distribution, which essentially they are Gaussian. And as you can see, the factor and the shift are basically the mean and variance of the Gaussian. So, okay, this is something that you can. There are already libraries you can use for this. Okay, so this is like training to do once the model for the likelihood, but then one thing that you can do is to do this sequentially. So in the case, for instance, of the neural posterior estimation, you already have the posterior, so you can, in the case of peregrine, you multiply by the prior, and you already have posterior. Here, what we have to do is, we have the likelihood, so we have to sample. And then the idea is that, so you train initially the neural likelihood estimator, and then you can draw samples from this, and certainly, so, well, and then you can do the posterior, and then what you do is that the next batch of simulation are based on these samples, and basically what you do is you retrain your model, which is much cheaper than the initial training, and you can do this until you converge into the solution. So then this method is very well adapted to when you have a single observation. So you're already detecting one signal, and then you want to concentrate on this. This is a good way of converging into it, and this is why this could be a good tool for the case of alerts. Let me see. So this is a similar scheme as I showed you before, but here what I want to tell you is two things. One thing is that the input of our, so we are training the livelihood, so therefore our input, so the livelihood has a dimension that is going to be of the same order as the data. Right? So you cannot just input all the data in a neural network because it's too large. So what we need is to do some compression before passing it to the neural network. And the other thing that I wanted to mention is that in principle you can use this with any representation of your signals. You can either use frequency domain, time domain, or you can use time frequency domain. At the moment, all what we have been doing has been in the time domain, but we are also working towards time frequency. So these are the two things that I mentioned. So one example where we have applied this is to the signals that they were in one of the previous Lisa data challenges, in the Sangria, for instance, where you have these signals are represented by the EMR phenom D model, where you have 11 parameters. This is the signal in the frequency domain. So we used to, as I said before, we have to compress the data. We have used two techniques. One is principal component analysis, and the other one is to use autoencoders, where basically autoencoders are neural networks that have this shape where there is so they start wide in the streams, and then you have here an arrow part, and then you demand that what you have in one of the streams is equal to the other one when you train, and so what you get in the middle is the latent space where you have the compression. So what we have found is that I mean, we have been using this, but with this, I mean, with a trivial type of architecture, we get a very good recovery of the spiral of the ring down, but not of the merger, where most of the SNR happens to be, especially for Lisa. So this is something that we have to improve. So we have applied this, and we already published this work. It's the first experiments that we have done, and what you can see here is a comparison with. This is using a typical mass course in Monte Carlo, in particular ERIN. As you can see, it recovers very well the parameters. This is what we do in our sequential neural livelihood with PCA. It more or less gives similar results to ERIN, not as good as ERIN, but similar results. While with the autoencoders, despite you only have basically the spiral, still you can recover some parameters reasonably well. Okay, so just to finish, just to mention that principal simulation-based inference is a promised technique that maybe we can use to build models for this global fit, or maybe even try to design alternative algorithms for a global fit model. When you use this sequentially, it allows you to focus on a particular observation, which is something that one can use to try to design some very fast algorithms, in particular to provide maybe alerts. We are now improving we are now working in several directions. One of them is to improve the autoencoders. What we have done is to try very different architectures. Now well, at least the compression part seems to be working. We recover all the parts of the signal properly, but we have not yet integrated this with the main algorithm, which we plan to do this in the next probably couple of months. Yes, we have also used coupling this to the noisers, etc., etc. So one of the things we have started to do is to what extent this can work with other representations of the data. As I said, in this work we use time domain, so we are now trying to see different time frequency representations, and here there is no unique possibility. But well, we are trying a few that have already been tested in LBK. How I'm going with time? Okay. Yes, of course. When using time frequency, then you can try also to use a bit more to try this in a more complex data, using maybe glitches, gaps, things like this. But then this requires to change several parts of the codes that we have now. So, but this is okay, something that we have thinking for the future. And finally, another thing we want to do is, instead of using the phenom-D, try to, because we are using it in the time domain, try to use phenom-T, which are the waveforms that are currently in the Mojito datasets, and try to then test these algorithms in the Mojito data. And basically, that's it. Thank you very much for your attention.
We do have time for one question. So I want to come up to the second.
Hi, thank you for the nice talk. So I was wondering if you could explain to me why the sequential neural likelihood approach doesn't constitute essentially double dipping, because you're using your posterior on the data, well, and estimating your posterior on the data to train your neural network.
We're using the likelihood. We're using our likelihood. What we construct is a likelihood. So then, in order to have posterior, we need to sample, right?
Right.
And then what we do is to sample, and with that, you get closer to the target. And then, with these samples, we retrain, but now very much closer to this. And then this process converges quite fast. Just because rather than, okay, I want to cover with likelihood the whole parameter space in one go with the training, which will cost you much more than doing this sequentially. That's a little bit the idea.
Sure, but if you're using your data to inform that training process, how are you not like incorporating multiple instances of your data into the final posterior that you're inferring? I'm trying to understand.
Well, when you do, with the posteriors, you use again the simulator, not the data. You use the simulator to retrain, because you are using new instances that were not part of the initial training.
Well, maybe talk after. Okay. Thank you.
All right, we can take our speaker.
Thank you very much.
So, next up, we have Aaron Johnson, who's going to be telling you.
Okay, hi everyone, my name is Aaron Johnson. I'm a scientist at National Marshall Space Flight Center, and today I'm going to talk to you about LISA Galactic Binary Catalog Metrics. There we go, okay. All right, so you've sampled your global fit, you have the output. What do we do now? So it turns out that you would like your global fit output to look like the thing on the left, but it turns out that it looks like the thing on the right. Why does this happen? So we have something called the label switching problem. So you are, if you have a model which has more than one of any type of source, the output of your sampler can store that as S1 plus S2, or it can store it as S2 comma S1. And the reason that this happens is because the likelihood depends on the addition of two models, and addition is commutative. So there's this global symmetry that you have to deal with. And so you need to do some sort of clustering to go from what is called fully converged reality back to something with independent source labels. There are other issues that you have to deal with. One is some of the signals lack individual identity, and also the number of signals is unknown a priori, so we have to use some sort of transdimensional sampling algorithm. All right, so in this work, which is not about clustering, but it is a part of this, and I needed to mention it so that we can talk about this slide. We use Sangria, we use the Sangria data set, we use the Erebor catalog and results from Michael Katz et al. And in this work, they used the waveform match method, which is by Littenberg et al. And the output samples in this catalog all have SNR greater than 7. There's some cutoff there. And on top of that, there's a threshold on what's called the confidence. The confidence is some measure of how likely the source is to be real. And so this is the number of sources, the number of times in your chain that the source is on, divided by the total number of sample entries in the chain. Okay, and so there's a confidence cutoff of 0.25, so it's greater than or equal to that. And all of the plots in this talk are going to look like this one on the right. So we have on this plot the number of sources, the number of injections, and this is just straight from the injection list from the Sangria dataset. And here we've split it up into the frequency SNR space. And so on the x-axis here, the horizontal axis, we have frequency in millihertz, and on the vertical axis, we have the injection SNR in log. All right, so the goal here is to compute catalog metrics. So there are a few players here. We have the true positives, or the catalog sources that have been matched with the injection list. And we also have false positives, which are catalog sources that don't have injections matched to them. And then false negatives, which have injections that were not recovered at all. So from this, we can compute two metrics. One that we use is called the purity, which is what fraction of the sources in the catalog are real. And then the completeness, which is what fraction are correctly recovered. Okay. Why do we care about this? Well, there are at least 4 good reasons. One is you can compare different global fit methods, so air bore versus glass versus GMU versus, and so on. Another one is you can find problematic regions of the parameter space for sampling. So this is a pretty important thing that we can do with this. We can find good parameter regions for electromagnetic follow-up. If you want to look for sources, you want to know where they're going to likely be pretty clean recoveries. And then we can optimize our catalog choices. For example, we can make a confidence threshold. All right, so throughout this talk, we'll use the highest density region a little bit. And so this is just roughly, you can say it roughly as, if you turn the posterior over and you fill it up with water, the part that's filled up is the percentile highest density region. On the right here, we have the HDI, which is like the HDR, but only one-dimensional. And this is nice because you can, you can deal with multimodal distributions compared to some other metrics. So the 0th percentile in this metric, the HDR, is going to be the maximum a posteriori value, and the 100th percentile is the extreme edge of the distribution. All right, so our procedure looks something like this. We start with the catalog. We cut based on the confidence threshold. On the Sangria injection set, we'll cut to SNRs greater than 1 because we don't expect to detect anything lower than SNR 1. And we'll cut the frequency, we'll cut the injection set to the ones that fall within posterior regions. We assume that anything outside of that is not detected. Okay, so we pick a catalog source, we fit a normalizing flow to it. We compute, it's a 6-dimensional normalizing flow. We can talk about this later if you want. Just find me somewhere. We compute the 6-dimensional HDR value. If that HDR is less than 0.99, then we'll say that we accept that injection as a match to the source, and then we'll remove the matched pair so we don't get more than one match per source in the catalog. All right, if there's no match, then we just say it's not matched and we go to the next one. All right, so from there you can compute the catalog purity and completeness. So on the left here, we have all of the injections with SNR greater than 7. And on the right, we have the catalog sources that have injections matched to them. Okay, so we've got a disparity here of maybe 1,500 or more. Yeah, this one on the right is the true positives. So we'll use that to compute these metrics. Okay, so let's talk a little bit about purity. And it's clear from the plot on the left here that we definitely detect sources better. We recover sources better in some regions of the parameter space. So on the left here, we have this typical plot, but there's a second panel. That second panel is a, so it's the number of injections with SNR greater than or equal to 7. And you can see here that the purity on the top there is worse where that bottom panel peaks. So if you have more sources, you get some sort of confusion noise. It's hard, your sampler has a hard time getting the properties of the source correct. And so you end up with some poorer purity based on that. And you can see here on the right, this is the false positives. These are the regions which are problematic. And you can see that it's right in that region where the purity gets worse. And then also there's a region a little bit above it, which is a little bit disjoint, around 8 millihertz, which is a little interesting. We're still investigating that one. Okay, well, there is a hint, maybe. 8 millihertz is where that green dashed line is here on the left panel. And you see that it falls just after the confusion noise. And it's sort of in this dip in the noise curve where we find this extra region. Okay, so for the completeness, we broadly find sort of similar situation here. You have better completeness outside of this confusion region at around 1 millihertz, 1 to 5 millihertz. And So on the right, we're showing the false negatives. You still have some in that 6 to 8 millihertz region, but you don't have quite as many. But you still find the same, that confusion region is still pretty bad. Okay, so I wanted to point out here that if you have one which has 0, so these are on the outside here, these are just like one source that's either correctly recovered or not. You can see the contours here give you the number of sources in each bin, and so it's just one in that bin up there in the upper left. But that is the loudest source in the Sangria data set, and so you'd really hope that we'd get it right. And very clearly, we have something here in both the purity, which means that it was recovered, so it's both in the completeness and the purity, which means that it was recovered, but incorrectly. Okay, so we investigated this a bit, and so here's what's happening. In one single bin, you have the loudest source, which is SNR 800, and you have two SNR 13 sources, which are skewing the properties of this signal. Okay, so if we look at the recovery, we missed the loudest source in Sangria. Glass missed it too, and so this would be a situation where the golden catalog didn't work and on the loudest source. So we have some work to do. So then the question is, what happened? Well, first of all, let me point out that the amplitude here is in the tail of the distribution. And then on top of that, the inclination falls outside of the posterior region at all. So the posterior that we recovered, the injection is completely outside. On the inclination, the ecliptic longitude. So if you wanted to find the sky position of this thing, you would not get it. It's not within the 90% percent region of the sky position, because it's not even within the posterior. And I just want to point out that this appears to be a sampling issue. If I try harder, start on the injected values, it stays at 3 sources instead of going to 1. It seems like what's happening here is there's some confusion issue where that single source that we get covers the power for all 3 of those sources instead of just 1. So I think that with better sampling, we may be able to recover this one. There's more work to do. All right, so I did want to talk a little bit about the purity with confidence cutoff, so that you can change this up a bit. We separated out the frequencies here on the right plot with different confidence cutoffs, and then we varied the confidence cutoff. And you can see that as you go to higher frequencies, you have better purity with higher confidence cutoffs. Now, this generally is true across frequencies, but you can actually get up to 100% purity if you go to higher frequencies and increase the confidence cutoff. And so I wanted to point out here that the purity against completeness, if you plot these things against each other and you vary the confidence cutoff, as these curves go down, you get worse purity, and so what you're doing there is you are decreasing the confidence. As you go up and to the left on these curves, you're increasing the confidence cutoff, and as you do that, you get higher purity. And so these values, which are about 0.6, are something like the values that you would use if you wanted to maximize both the purity and the confidence. And so anyways, this can give some information on how you would choose the confidence cutoff to get a good set of a good catalog. All right, so in conclusion, I'll just leave these up here. I think I'm out of time, but yeah, the next step is basically just to work on the sampling issue, see if that actually is what's causing the problem. And thank you.
Okay, I think we have time for one quick question. If not,
Petra. Yeah.
Okay, we have probably time for another quick question. If not, I'll ask one.
Yeah.
Okay, I'll ask one until someone decides they want to ask one. So you have these sort of 2 metrics that you're kind of looking at right now, which is just the purity and the sort of completeness. But given that the loudest one you saw was definitely there, just biased.
Yes.
Are you guys starting to think about having a 3rd category to at least tell people that it's more than just a purity? Questions like this, so there's actually an issue with the catalog, that there are things there, but they might not be with the right exact parameters.
Yeah, I mean, that's a good question. You could imagine extending out the posterior somehow, or posterior region or something like that.
Or having some booster threshold that will help identify, okay, there's actually is something there in the global fit, but it's not really recovered correctly.
Yeah, so we haven't done this yet, and really the goal of this project was sort of to say, okay, you know, like, if an astronomer were to look at the catalogs today, what would they get out of it?
Right.
And it seems like we really need to deal
Well,
with
I
this.
think if they saw it today, they'd get that loud one.
Right.
And maybe it doesn't matter if it's a little wrong.
Yeah, well, I mean, it depends on how much they believe the posteriors, right? And I think that was the question that we were trying to answer, but you're right. I mean, doing something that sort of smears out the posterior maybe would help. Yeah.
Okay.
Thanks.
Thank you so much.
Okay. Hello, everyone. My name is Levi Schult. I'm a fourth-year graduate student at Vanderbilt University. Today, I'll be talking about some work I did with Alexander Criswell, who's a research faculty at Vanderbilt, as well as my advisors, Steve Taylor and Katie Brevik, who's a professor at Carnegie Mellon. So, I'm going to be talking today about cataclysmic variables. These are a class of galactic stellar binary that's been pretty overlooked in the LISA community. I asked someone who's been in the field longer than I have as to why they've been kind of ignored, and he said it's because they're wimpy. But they are wimpy no more. Let's see. Okay, so first things first, some definitions. What is a cataclysmic variable? So this is a white dwarf with a main sequence companion. The white dwarf is accreting matter from the main sequence companion, and depending on the magnetic field of the white dwarf, they do some interesting accretion flows, but they do some things that are kind of, well, at least not traditional to me in my background from pulsar timing arrays. So I thought I'd take us through some of their evolution. So on the y-axis, we have the donor mass, and on the x-axis, we have the gravitational wave frequency or orbital period. And so starting from the left here, the donor is losing mass as it's being accreted by the white dwarf. This continues for a little while until we reach an orbital period of about 3-ish hours, at which point the donor star becomes fully convective, magnetic braking turns off, and the bloated main sequence star is actually able to shrink back down to thermal equilibrium, loses contact with its Roche lobe, and so long story short, mass transfer stops, and you have this period where it's a detached binary. That's this middle region where the binary evolves purely due to gravitational wave-driven evolution. And eventually, the orbital separation shrinks enough such that the donor star can make contact with its Roche lobe radius again and overflow onto the white dwarf. So mass transfer restarts. It's found by EM surveys. And this continues until the donor star reaches a low enough mass that it becomes degenerate, and in response to mass loss, instead of the radius shrinking, it actually increases, and because the stars are tidally locked, you actually see the binary orbit out spiral instead of in spiral due to the radiation of gravitational waves. So the CVs in this kind of high gravitational wave frequency minimum orbital period, these are what's known as period bouncers once they start out spiraling. I'll get to those in a second. So what sort of astrophysics can we do with these systems? So as you might have picked up from my explanation of their evolution, our surveys are very inhomogeneous and incomplete. It very much has to do with the mass transfer rate that is occurring in the cataclysmic variable. So there's a lot of questions around their space density and the true number of CVs in the Milky Way. A lot of our EM surveys are also missing the period bouncers, which we expect to be the vast majority of the population of CVs. We'd also like to learn more about magnetic braking, which is one of the methods for angular momentum loss in the system. And they may be a primary formation channel for AM Canum Venaticorum, which is a binary star system that's been studied a lot more in context for LISA. So some background in the previous work, there was this study, Scaringi et al. 2023, which looked at a population of CVs in the local Milky Way, kind of a kiloparsec solar neighborhood, based on local measurements of the CV space density from Gaia DR2. So that's this green population you're seeing on the left. You'll see that kind of gap there. That's the EM gap where the systems are not mass transferring. So they don't have any systems in there. That's something we'd like to rectify. And then on the right, you're seeing the gravitational wave imprint from their confusion stochastic gravitational wave background created by all of these CVs. So first things first, we wanted to fill this EM gap, and to do this, the CVs are evolving due to purely gravitational wave-driven evolution. So we can simply create a Gaussian kernel density estimator for the CVs in that last frequency bin before the gap. We can take that KDE and evolve it according to gravitational wave-driven evolution at each frequency bin throughout the EM gap. So that gets us this nice joint distribution in frequency and chirp mass space from which we can draw parameters. Of course, this looks pretty choppy, so we can smooth it with a one-dimensional interpolation over the frequency space. We can do some rejection sampling here and then normalize by the number of CVs that are in the last frequency bin to get a nice distribution of binary parameters through that EM gap. So then we can inject it into LISA data using BLIP, or the Bayesian LISA inference package. This is a software suite made by Alexander Criswell and Sharon Bonagiri that enables isotropic and anisotropic analyses of stochastic gravitational wave backgrounds in LISA data. You're able to inject arbitrary populations and also perform inference on them with whatever bespoke spectral model you might want. It's very easy to use. I recommend everyone try it if you're interested in stochastic gravitational wave modeling in LISA. So we can inject this population of cataclysmic variables into a Fourier LISA mission. For our control, we're going to be using a fiducial double white dwarf population from Thiel et al. 2023. So here in the dotted green is our CV population from the local Milky Way. In dotted blue here is our fiducial double white dwarf population, and then in the solid blue and green is the power spectral density that we would see in a Fourier LISA mission. So the solid blue is just from our control, only double white dwarfs, and green is with the CVs. You might notice there's nothing really there. This was kind of surprising to us. This is pretty different from the Scaringi results, so we're still looking into this a bit, but we also realized, I realized that these are in different conventions, but the important thing is to notice there's a bump here and there's no bump here. But this isn't really an apples to apples comparison because we're looking at a whole galactic population of double white dwarf binaries versus a only local population of CVs, so we wanted to expand this out to the whole galaxy. So we can do we can create a population of cataclysmic variables for the entire galaxy just using the same basic space density estimate from Gaia DR2 and also with a Macmillan 2011 or Breivik 2020 galaxy model that's just a bulge and a disk to create a galactic population of CVs. We fill the EM gap again using the same gravitational wave-driven prescription that we talked about before. And then we can inject this into Fourier LISA data, and now we do see a nice little bump here in the spectrum. So again, the dotted green is our galactic CV population, dotted blue is our double white dwarf fiducial population, and then the green here is our PSD when we have these CVs that haven't been previously included. So this is obviously decently concerning. If you don't model for these, they're probably going to bias your foreground fits and hinder the kind of astrophysics you want to do with the galactic binaries in the foreground, and also could affect, this is the region of frequency space where the foreground is the dominant noise source, so any imprecision in your models is going to affect your astrophysics for the other source classes. So we wanted to see exactly how much does this affect your spectral fits. So we did some spectral fits on these two data sets. The solid lines are the median, and then the shaded regions are the 95% credible intervals. And you can see that in the green spectral fit, which is on the data set that has our double white dwarf foreground and the CVs, you get this immediate bump due to those unmodeled cataclysmic variables. So this is something that cannot be ignored any longer, really. There's a lot of things we'd like to investigate next. Specifically, we're trying to spectrally model both populations and see if we can separate them. But that can be very difficult since the cataclysmic variables and the foreground have the exact same anisotropy on the sky. So you can't actually gain any distinguishing power from their spatial distributions. So yeah, there's a lot of questions we have. The spatial or the spectral separation may require astrophysically or EM derived spectral models. This is also a very simplistic population. There's ideas to maybe do some real binary population synthesis that have consistent prescriptions for the double white dwarfs and the CVs. But yeah, so just some quick summaries. We simulated a local population of CVs and filled the gap from electromagnetic surveys and found that the local population of CVs doesn't really make an impact on a 4-year lease emission, but a galactic population will. And yeah, they are wimpy no more. We have to model them. We have to include them in our analyses and in our simulated data sets as well. So I wanted to thank the organizers for giving me the opportunity to speak, as well as the LISA Travel Grant for supporting my ability to come out here. So thank you very much.
Okay, we do have time for some questions.
Very nice talk. Like the other backgrounds, I'm just wondering, maybe you haven't looked at this yet, but I just wanted to ask, is there anything you can learn about the population from LISA? So kind of going backwards from, seeing the effects on LISA, can you actually learn from it?
Yes, yeah, so the big thing is the CVs we know about are very incomplete in their distribution and where we're seeing them. So the hope is with detecting them in LISA, we can get a better estimate of the space density and the scale height of these populations as well. They're expected also to have, similar to other galactic binary populations, have different scale heights according to age. I'm hoping that with enough time and maybe with really good spectral modeling, you're able to tease out things from the actual spectrum, depending on which portion of the population of CVs you're actually looking at, depending on their evolution, that sort of thing. So I think there's definitely astrophysics we can pull out. Some of it may also depend on the resolvable CVs, but at least from the things we've seen so far, there aren't going to be too many resolvable.
Thank you. Thank you, very interesting talk. Just to understand, what do you call spectral fit? The shape of the...
Yeah. So this spectral fit is just our model for the gravitational wave spectrum kind of thing. But this spectral model is pretty bespoke for the double white dwarf population. So this is just kind of seeing what biases are introduced by not model, in the case where the CVs aren't accounted for in our models.
Yeah, then I'd just like to comment, because I think you said something to the effect that it may bias the recovery of some sources. I don't think it can bias more than the conventional foreground, because the level of the noise is one of the parameters that's being fit for in the global fit.
Mm-hmm.
What it can bias, and probably Alexander can say it better, is population inference.
Yeah.
But I don't think it will bias the recovery more than the regular noise.
Yeah, I mean, I don't know what this would say in your, when you do the population inference. That bump is gonna say something else about your double white dwarf population that probably isn't true. So yeah.
Thanks.
All right, let's thank our speaker. All right, so up next we speak of the devil. We have Alexander Criswell who's going to be telling us about population inference.
Okay. Hi folks, I'm Alexander Criswell. I'm research faculty at Vanderbilt University, and essentially today I'm going to try to make the argument to you that we have to do population inference inside of the global fit, which is not necessarily something that we all want to hear, but I would rather us figure that out now instead of in 10 years when we have a detector in space. So, perfect. This is LISA data, or at least the bit of the LISA data that I'm interested in today. We've got a bunch of white dwarf binaries that are individually resolved, and then those are bleeding down into an unresolved stochastic foreground that we just heard a good deal about. We want to do, or at least I want to do, some kind of astrophysical population inference. I think we all want to do this. It's in the LISA science objectives. We have the opportunity to learn about all sorts of things, talking about common envelope evolution, other aspects of low-mass stellar evolution, opportunities to learn about the Milky Way galaxy itself, and more. But the way that we've traditionally done this, which is to do population inference of compact binary mergers in the LBK, relies on a certain set of assumptions. I'm not actually going to go into detail on any of these right now because all of them break for LISA. But the ones that I really want to focus on are these two ideas of transdimensionality and circularity. Okay, so the first one, this idea of transdimensionality, we've been talking about it all week. The global fit is transdimensional, and a consequence of this is that the set of sources that you actually infer to be present in your data is dependent on the model that you set out to use when you are running the global fit. So if we consider a situation where we start with some model, I'll call it model 1, we run the global fit, we get a certain set of in this case, resolved sources. If we choose a different model entirely, so a different prior on our set of galactic binaries, we are going to actually get a different set of resolved binaries. And the problem comes about when you run your global fit with model 1, and then you turn around and say, I want to reweight that, the posterior under that assumption into a posterior if I had assumed model 2 to begin with. Because you have sources that don't exist. You have no posterior density for sources that you would have actually detected if you had run your global fit with model 2 to begin with. And actually in Neil and Tyson's 2023 paper where they demonstrated the glass UCB sampler, they found, they were setting out to actually set themselves up in the future to do this exact kind of resampling that we do in terrestrial gravitational wave detectors. And they set a completely uniform prior on the sky location of the galactic binaries, whereas previously they'd been using a galaxy-shaped prior. And what they found really surprised them because their detection efficiency dropped. They missed a whole pile of sources by assuming an agnostic uniform prior on the sky that they were detecting if they actually had assumed that the sources were distributed the way that we think they probably are, which is to say in the shape of the Milky Way. Second problem, which has been talked about a fair bit, there was a nice talk by Cohen Rondell on Monday and Ariane Ranzini on Tuesday, and I think John yesterday, pointing out that you have this problem for the population when it comes to galactic binaries specifically, and that's you have this situation where your ability to resolve a particular galactic binary is dependent on a couple things. It's dependent on the parameters of that binary, it's dependent on the instrumental noise, and it's dependent on the level of the confusion foreground. But the level of your confusion foreground is determined by how well you're managing to subtract individual sources and resolve them out of the foreground. So you end up in the situation where your resolved systems are dependent on the population and dependent on your unresolved foreground, which is dependent on the population and dependent on your resolved sources. And you go around and around and around and around. And if you want to do population inference with LISA sources, you have to account for this in some way. So earlier this year, John Gare and Alexandra Subiana put out a nice paper that was basically showing, okay, if we want to go and do this in post, they figure out a way to deal with the circularity. They don't figure out a way to deal with this. So this is still a problem. But they figure out a way to deal with the circularity by essentially defining a function that they call a resolvability function, which says, okay, I think I know I can make a model of how we divide this circularity and the resolved and unresolved binaries. Now the problem with that is that you have to make a model choice at that point, and you have to make a model choice that is actually not informed by the data and isn't an astrophysical model at all. And even in their paper, they show that if you make the wrong choice of that resolvability function, you get biased results in your population inference. Okay, so I'm worried that we're going to have problems with this. I'm especially worried about that first point, about the transdimensionality. And so the paper that we put out basically says that we should do galactic binary population inference within the LISA global fit itself. So we set out to do this. Now, I know this sounds like a daunting concept, and it actually goes a bit in the face of what we've been planning largely as a mission in terms of the NSGS and the DDPC will run a global fit, and then we will do science interpretation all downstream. But I think it's actually a really good idea to do this in the global fit in the first place, and that's largely because once you understand that your foreground and your galactic and your resolved galactic binaries are in fact not two distinct populations, but they are all coming from the same population of white dwarf binaries in the Milky Way, and they're just showing up in our analysis differently depending on how we choose to treat them. You realize that you can use your resolved binaries to supercharge your foreground estimation, which is what Ariana was talking about on Tuesday. On top of that, if you're self-consistently modeling both your foreground and your resolved binaries, you get, as a very nice side effect, a prior, an astrophysically motivated prior, on the number of resolved binaries that you expect to get out, the number of subthreshold systems that are contributing to any non-Gaussian entity in the foreground, and all of this together means you get an improved global fit, which means you do every single Lisa science case better. So I think we should do this. All of that, though, is contingent on the idea that you're actually getting your population model right. So there's danger here. But we're doing it anyway, damn the danger. There's a paper there, I'll put this QR code up at the end as well, that we put out earlier this year, in which we detail a prototype population inference block for the LISA global fit called Pelargir, which is population estimation for LISA in a reversible jump global inference regime, or just a convoluted Lord of the Rings reference. And the way it works is just like any other population analysis. We want to sample from some set of population parameters. We then draw an entire galaxy from that population. We actually do this in the published results. We do this about 300 times per likelihood evaluation. And then we have to model that circularity. The way that we do this is we developed a rapid sorting algorithm. We leveraged the fact that we know exactly what is in our simulated population because we made it. And then in each frequency band, we can do some fancy sorting to basically condition on an SNR threshold, as we did in the paper, or an amplitude cutoff, or really what you should do is parameterize what that division is and allow the data to tell you what it looks like. But once we've done this, we've got some set of resolved systems from our simulation, we've got a foreground from our simulation, and then we can compute the likelihood based on not our resolved binaries from the simulation, but our actual current state of the resolved GB sampler, conditioned on the current population prior, the Poisson statistics of the resolved binaries, which we can learn from our simulation, and the foreground spectrum itself. So for the initial paper, what we really wanted to do is work out the statistics and then make sure that our statistics were right and our approach was actually going to be successful. We decided to not try to build an entire global fit from scratch to test this, and not to immediately dive in the deep end and introduce 5 million other problems that we would have to troubleshoot to make sure that our statistics were right. So we built a toy model, and basically it's meant to emulate one block execution within the global fit. So we take one state of the galactic binary sampler, we take one state of the instrumental noise, and then we do one inference run of our population model, which is built on top of the foreground estimation as well. And it works, which is great. So we get back that population-informed prior on the resolved binaries, which agrees with the number of resolved binaries in the current state, simulated state that we passed it. We get a very nice foreground recovery. This is essentially an astrophysical non-parametric model. It can take not exactly any shape you choose, but it can take, it is not bound by any particular parametric shape to do this. It's just that the astrophysical processes that we are modeling produce a galactic foreground shaped thing. Now you notice that our simulated toy model likelihood has 2 sigma uncertainty out to there, and the posterior is quite a bit narrower. This is telling you that we're successfully pulling in quite a bit of information from our resolved binaries and from the other population level statistics to get a better foreground fit. This is great news. On top of that, and these posteriors are completely undersampled, I'll talk more about that in a bit, we are able to successfully recover, or at least we're able to successfully recover all of our population level parameters. We had a simple model on the binary masses, a simple galaxy model, and the just assumed a power law distribution for the orbital separations of our binaries. Some of these are constrained, some less so, some degenerate, but all within the 95% credible intervals. Cool. Now this, to me, is the money slide. When I looked at this, when this worked for the first time, I literally did the thing where you like kind of jump out of your chair and fist bump at the sky. Because what it's showing is that we are successfully recovering the distribution of the full population. These distributions that we're fitting in kind of the mauve there can take the shape of the green histogram, with the exception of the galaxy, which would just like way overshoot it up here and can't quite get this whole spike. But in black is the distribution of the actual full population. And so we're handling all of that, well, not transdimensionality, this is a toy model. We're handling all of that circularity properly and essentially handling our selection effects properly to be able to recover the full population. So this to me said, great, our statistics are working, phenomenal. Where do we go from here? We've got a working toy model, which is actually quite a ways from being a thing that you can plug into a global fit. First thing that we need to do is plug this into Blip, which Levi nicely gave you all a primer on, to be able to do realistic stochastic analyses with the foreground and actually connect in that anisotropy piece as well, because the time modulation of the galaxy in the LISA data, thank you, is driven by the anisotropy of the galaxy, which is driven by the shape of the Milky Way, right? We really need to optimize this. I showed you undersampled posteriors because that was the best that we can get in the time that the university would give me the GPU for. We built a really fast analytic way of doing this, and it is not fast enough to simulate 300 galaxies of 10 million binaries, every likelihood evaluation. So what we have done is we've built a really good way of making a training data set for a normalizing flow emulator, which is what we're working on now. Okay, that's the talk. I'll leave my summary slide up with the QR code to the paper, and I'm happy to take any questions. Thank you.
I was wondering how, because we have non-causality, how would your work be affected if you use hyperbolic field?
This is a good question. I don't know. I would imagine that we could create a mapping between the expected amount of non-Gaussianity and the behavior of the hyperbolic likelihood to give some sort of prior on what we should be doing. But I would have to think further about this. But Nikos Karnisis dropped a line to us and is interested in figuring this out. So more details whenever we get around to that.
There's a code by Arturo,
Mm-hmm.
it's called Hyperwave, which
Yeah.
does have to look like this.
Yes.
Oh, thank you.
Any other questions? Okay, let's thank our speaker. All right, let's welcome, next up is Stefan Strub.
Hello everyone. I'm here to present you a new global fit pipeline. We call it Umbrella. Like we have a bit of a baptism today, so this is it. So Umbrella is operating on the newest dataset. It's on Mojito Light. And Mojito Light, as maybe you saw in Tyson's talk, where it has a lot of new signals. So we have the galactic binaries, massive black hole binaries, Emery's, stellar origin black hole binaries, and noise. And so far, we only focus onto the galactic binaries and the massive black hole binaries, and other sources are a problem of the future. It's already complicated enough. And at this point, I would like to say many thanks to the TTPC for generating this data, making this data challenge feasible. And here on the bottom left, you see the data in the time axis. On the right, you see it in the frequency domain. So here you see that this problem is in the time domain, the noise is dominating the galactic binaries, but you see the massive black hole binaries very well. And whereas in the frequency domain, you see the galactic binaries are dominating very much. So how can we tackle that problem? So we can either improve the computational hardware, but this is eventually not feasible because now if we have really the data, we would like to spend probably tens of thousands of US dollars on a solution of it. But if we are still in developing and research phase, we actually would not like to spend that much money and time on it. So we would like to speed up things. So we can speed up either the waveform generation, which we need for a function evaluation. So this is what we want to do, get Bayes theorem, and we are interested a lot in the log likelihood, which is this one here. And for each evaluation of this function, we need to generate once the waveform, and that costs a lot. So you can either speed it up with jacks or GPUs or other ways, but this eventually also probably hits a limit. We see it now with Mojito Light. Massive black hole binaries are very slow, takes roughly 1 second or so. And then the other way is to speed up the scalar product. For example, in the frequency time domain, you can do it. And what I'm mostly interested in is how can we speed up the whole pipeline by itself by using fewer function evaluations. So what we do is a bit of a difference between here. We have on the right side the Bayesian posterior distributions, which use a lot of function evaluations, but you get a posterior. Whereas on the left side you have the maximum likelihood estimate, which uses fewer signal simulations, but you don't get a posterior. And what I suggest here is to use a hybrid method where you use the result of your maximum likelihood estimate as an initial guess or a proposal distribution for MCMC algorithm. And how do we do that? Let's go first into the galactic binaries, because in galactic binaries we have the issue that we have a lot of them are overlapping. And how do we do that if we are not doing it all at the same time? So we can first, in this one, for example, here is in black the data, and in gray you have two signals in the frequency domain, zoomed in. And when you search for one first, let's do it in hierarchical first. Tyson also mentioned that way, but it gets into some issues, as we see soon. So if we first detect one, and this is the blue one is the one we recover, and then in red we have our residual, and we can analyze that again, see what we get out. We get this orange one out here, but here we see that the residual actually is still a bit higher than on the other sides. So that suggests that we actually have a bias and we're not properly recovering these two signals. So what we can do now then, or this is exactly the issue if we do it in a hierarchical search, or where we just sequentially subtract the signals, we can use these two signals as an input of a joint search. And that then removes this bias here. We see the recovery matches really well, and the residual is at the bottom. And let's see how much time we have, 5 minutes, lovely. So this is a bit quick down here. So what do we do if we have hundreds of them overlapping? This is in the real data challenge. So all these black lines are different galactic binaries, but we see only the black one in data, sorry, the gray ones are binaries. And here you see each dot represents one signal. So what we can do, we can split up this frequency domain into different segments. I highlighted them here in blue. For example, these are two non-neighboring segments, so we can call them for example, odd and even, separate them, and when we label them through. And we search first in the blue ones, and also with some tapering, so that's why we still recover this orange one here, but this orange we don't trust it. because it's outside of our interested field. So we actually only thrust into the blue one and subtract here the blue one and here the red one. And then we get our residual is then the CN line here. And then we can search again with the CN line. Here we see these two signals are subtracted. We can now switch to the odd ones and search again. And this is what we get out. And then after that, because at the very first beginning we still had some bias of the neighbors here in the odd ones, we have to research again the even fields, but with the residual this time. And then we can sum it up together and combine the results. And now this is shown here only for 4 segments, but we do this for, I think, 7,000 segments throughout the whole frequency band. And this is how we perform across it. So this is now with the Mojito Light dataset, so it's very exciting. And we do it with using ChatGPT, so shout out to everybody which developed on that. And we are able to do that with only 750 million function evaluations. It still sounds like a big number, but trust me, it is very little. So we're very proud of that. And because we can do that with only 115 CPU core hours, so roughly $3 in cost, and we can run it in parallel if you get access to multiple CPUs. And yeah, so we can also get all these signals. So we get around 6,000 signals if we sum these two numbers together, and we can then match them with our injections because this is simulated, so we know what we put in. And this is our, we show it here now with the overlap, which is defined as such. And each blue one is one which matches well with an injection. And each orange one is a recovery which does not match well. So here we see that most of these which are not matching well are in the bottom with a lower amplitude. And all the green ones are signals which are injected in the data set, but they are not recovered. But they're also really not recoverable because they've built the galactic foreground. So that was the first step, and now we do it in a second step. Like I said, we can use this, our best fit solutions to get a joint posterior distribution. And here what we do, we group them first into we simulate each waveform which we recovered and see if they overlap in the frequency domain with another waveform. And if yes, then we put them in the same group. And this we do then with all the 6,000 signals which were recovered. And these are the groups which we see here. So actually 1,200 of the signals are by themselves. They don't really have a neighbor with which they are overlapping. And they're the largest group has 22 signals inside. And that is a feasible amount for a joint posterior. And we used Erin for that, sorry, here. So quick shout out to Michael Katz for that, mostly. And, wrong direction, sorry. Yeah, and then we used Erin to show that it's possible to speed it up. And then now we can do that with only 40,000 function evaluations. We can get a posterior here, depends on how you do it, with how many temperatures and such. And now I also promised you some massive black hole binaries. So that was a very tricky part because, like I said before, with Mojito Light, massive black hole binary waveform generation got really slow. So I needed to tweak the algorithm a bit, but essentially we got it down to be found, the actual do the search with only 20,000 function evaluations. So it would still if you're on a slow core, single core, it would be 20,000 seconds roughly to search for it. And they're also, here you see, it's performed on all 20 massive black hole binaries, which we have in the data set. They're not all perfect. For example, this one you see here. I think it is because the frequency is a bit too high, and we cap it now at a sampling time of 10 seconds. So we probably need to go lower, but that would also take everything like slower as well. So that's a bit of a trade-off right now, but this kind of shows that we probably need even like lower sampling time. But here on the right side, you see the signal which is indexed by 18, which is like the current focus of the data analysis challenges. This is the first signal here. And this one, as we can see visually, it actually matches quite well, like the injection in green. And what we have here in dashed red is our recovery. So this we can then perform in a global pipeline. I don't go too much into the details, but this is like a small scheme of the wheel. But we only have the noise, the galactic binaries, and the massive black hole binaries in this type now. In the future, we would also include more sources for that. And the idea as well here is that we don't currently the wheel would spin multiple times around, but here the idea is a bit different, that I spin the wheel, but as soon as the new data arrives, I update my data, So the data gets longer, but I use the previously found parameters to subtract them on the updated data. So it wouldn't just say I limit my wheel to spin 10 times around. No, I kind of constantly would spin it around, and then as soon as the new data arrives, I spin it again, kind of. So it's like a time evolving LISA global fit. So yeah, this is our conclusion. So we got quite a fast algorithm, which costs very little. We showed that we can use these estimates in a reversible jump MCMC effectively. And that is very good news, because why is this the first pipeline which has shown some results on the Mojito Light dataset on the search, which is probably because this is actually very costly, but this pipeline makes it cheap. So it speeds up the whole research process as well. So in that case, I also invite you to use it. It will be public soon, but if you reach out to me, it is already public. I'm happy to share with you. So it likely will speed up your whole process as well if you're into the data analysis side. And yeah, in the future, I would also like to include Binaries and data gaps, and also put it into time frequency domain. So there's still lots to do. And yeah, thank you very much, and join me under the umbrella.
Okay, let's take a question.
Very interesting work. I was curious, how are you choosing those frequency regions, and what happens if your source is on the edge of them?
Right. So the regions are chosen to be rather small. So I choose them to be 2 times the width of the widest expected signal. So each signal has a bandwidth, right? And I chase it 2 times to have sufficiently wide, but then as small as possible. And what happens if it overlays is, for example, here, the orange one signal here is a very good example of that. So let's see what happens. So yeah, here since it is in the even one, it gets subtracted right away. So maybe this is a bad example. Or yeah, let's go for it. So here it's gets subtracted right away. Here it is also subtracted, so it's not an issue. And then I research it again. So here, for example, that blue signal, or later orange, sorry, here blue, initially has a lot of overlap with these signals over here, right? Which is an issue, as we can see in the very first run. We recover it as such. But then once we also analyzed the odd ones and subtracted them, we can like analyze it cleanly without the inference of these signals over here.
Thank you.
Okay.
My question is, how do you define the overlap to construct the groups?
Yeah, yeah, good question. I did not mention because of time constraint, but it is by, yeah, it is a bit dirty, yeah. So what I do, I calculate the median of the waveform and then divide the median by 2, and everything which is above this threshold is basically my edge points. So let's say, like, for example, in this signal here, like half of the median is probably around here at these levels. So that would be my edges of the waveform. And then everything which is like in between, so for example, these two would be in the same group, I would say. Yeah.
Thank you.
Okay.
All right, let's thank our speaker. Okay, last speaker of the session, last but not least, is Lorenzo Sala, and only if I can get to your, oh no.
Okay, perfect. So thank you very much, first of all, for being here at this last talk of the ISA Symposium. And okay, so this talk is about some work that we carried out with a few people within the ISA performance and operations group, and this is the list of the people that work on this. And the topic actually is a bit different from the previous one. The topic is on ground, so the problem is the verification of the requirement of LISA. So the requirements of instrumentation, that can be requirements on the voltages, on the magnetic fields, on instrument stability, etc., and so on. And as an example, I just took one of them. The requirement that you see here is the requirement on the actuation, on the acceleration on the test mass caused by actuation noise, so voltages, instabilities, etc. And the problem is that we have to test for the requirement on ground. So this kind of effect would be transferring directly to the gravitational strain measured by LISA, so we have to test before launch. And just as an example, as we don't have measurements of this kind of effect yet, we will have in the next few months, years, etc. I just took as an example what happens if the, let's say, true value, as I'm using it in a simulation, what happens if the instrument is performing 4 times better than the requirement. Okay, if we could measure for a very long time, for instance 10 days that we can not have on ground for measurement, then we would see with the wedge periodogram that the instrument is performing well, but we don't have that time, so maybe we have like 12 hours, that is here, so 12 hours is 40,000 seconds, and with that we can measure at all frequencies, but in any case you see that it's very scattered. So the problem is that at this, with this short time measurement, we just have a few periodograms to average on. For instance, with 1 day, we have 3 windows. With 12 hours, we have 1 window, etc. This problem is not regarding the high frequencies. As you can see, at high frequencies, maybe you cannot see, but at high frequencies, we have many windows to average on, like hundreds, like thousands, so there is no problem. But the problem is the low frequencies, and the first problem that we face actually is statistics. So the PSD is very scattered, as you see here, and we have to understand how to understand if this measurement, that is maybe the only measurement that we have for this instrument, is or is not compliant with the requirement that it has. So the first thing that we can say, that we can see, is that given a true PSD, then the measurement of the PSD is distributed like a gamma function, so like a gamma distribution, sorry, so like this, for example. And this is with a few periodograms. And actually, if we have just one measurement, for instance, then we have to make an inference. We have to make like a Bayesian inference on the posterior of the theoretical value of the PSD that we have to. Is it good? Yeah, that we have to actually compare with the requirement. And the problem that we see is that with a few periodograms, like 2 periodograms, the posterior has very heavy tails. So the probability that we have that we measured a PSD of 1, but the posterior of the theoretical, but the actual value of the theoretical PSD is much higher, like 5 or 6, is pretty high if we have just a few periodograms. And so this is actually margin that we have to take into account. For instance, in the previous example, with this one, if we should apply this kind of margin, we would end up here. And this is thing that we have to be aware of, and so we have to understand how the statistic works in the end. Actually, this if we had like 95% probability on each of them to be compliant, on each frequency to be compliant with the requirement at that frequency, that would be not enough, because actually we need that the entire spectrum is compliant with the requirement with 95% probability. So each frequency should be compliant with a much higher probability, and that is actually a problem. It means that we would need very long measurements, and like, for instance, 24 hours the situation improves, we probably would need even more, so we have to find a way out. The solution to this problem to this specific problem is that we can choose the segment duration t, so that the number of periodogram increases actually with frequencies, so that you see that the situation is improving if we can use different segment duration from different frequencies. Another problem that we have to face is that the stretch length actually affects the frequency resolution. So, for instance, we cannot use the first four elements of the DFT, because otherwise we would end in having spectral leakage that we don't want, actually. So for at least we have to measure for 40,000 seconds. That way I'm using the 12 hours as a reference to measure just at the lower bound of the LISA measurement band, so the 0.1 millihertz. Another thing that we have to face, the last one, is that we don't want adjacent frequency beams to be overlapping, because we want to multiply probabilities, so we want them to be as independent as possible. So in addition to choosing the stretch duration, we also have to choose the DFT index increasing with frequency, so that they are as independent as possible. And so actually we chose a set of frequencies. We chose a set of 230 frequencies in the LISA band, so from 0.1 millihertz to 1 hertz. And for each of them, we have the segment duration that is changing. And in addition to that, we have the DFT index that is changing, so that the frequencies are almost as much as possible independent, let's say, and so given this frequency scheme, then we can measure, for instance, for 3 hours, for 12 hours, etc. And you see that the error bars are always narrowing down to the actual, let's say, true value that we have used in the simulation. So now we can we can actually go on to the actual definition of the requirement as that we set. So actually, we're choosing a global requirement on the global probability. So for each frequency, we divide in stretches and we measure the PST, and then we make an inference on the posterior of the theoretical PSD that is behind the measurement. And we analyze what is the probability that the theoretical value of the PST is actually compliant with the requirement, and this has a nice closed form, and we multiply that probability. So actually, we have a total probability that the instrument is compliant with the requirement, and we have to compare that probability with a certain threshold. For this first issue of the technical note of this work, we chose this threshold to be 95%. Now we are also going on with the analysis, etc. So we will understand if this 95% is okay, or if we have to make adjustments. In any case, this is an example. For instance, with the 12 hours measurement, you see that the measurement is not passing the requirement because this total probability is too low, and the problem is probably the first one. So you see that the probability that the first frequency is exceeding the requirement is really too high. So maybe we can measure for another 12 hours. This is another measurement, another simulation of the measurement, of course. And you see that this again is not passing the requirement. So probably for this kind of measurement, we should have to measure a little bit more. For instance, if we measure for 12 hours instead of 12, this is pretty clear that it is passing the requirement with a high probability, actually 0.999. So this is actually the conclusion that the test would be passed in 24 hours. That is much better than actually what we saw in the first slide with the Welch periodogram. It didn't look like exactly passing the test, whereas actually it is. And having a global probability instead of having single probability for each of them is beneficial, as we can afford a high margin as we have pretty good statistics at high frequency, so we don't need so high a margin at the high frequencies, but we need to transfer that margin to the lowest one, so that globally the measurement can pass the requirement with, let's say, a little bit more flexible probability. For instance, we also analyzed the LISA Pathfinder measurement. Just to give an example, you see that the LISA requirement would not be the measurement would not be compliant with the LISA requirement with the 4,000 seconds measurement, but it would be with 60 hours. Actually, the reference run of LISA Pathfinder lasted about 14 days. So I mean, in LISA Pathfinder, it was not a problem at all to have long measurements, but the problem is actually on ground with many instrumentation. One very last slide is about a step forward that we will have to work on. That is the narrowband stochastic processes. As the problem that we have to face is that on ground we cannot measure again for long time, and so we don't have enough resolution to detect narrowband stochastic processes if they have a small width. For instance, here you see some stochastic processes with the same amplitude but different width, and some of them you cannot detect if you have the measurement that is too short. So we have to understand that the instrument may have narrowband stochastic processes that are very very narrow, but we cannot detect them on the ground. So maybe the requirement that we chose to apply in this case is that we do not want to have single point, let's say, lines in any case, because we cannot measure their amplitude if we're limited by the frequency resolution. And this is actually the conclusive slide. So so we identified this kind of algorithm, and in the next future we will receive the feedback from many contractors and experimentalists that will have to apply the algorithm for the verification. And so we probably will change something, probably not. In any case, if you in the audience, if you're an experimentalist working on that, we would like very much to receive any feedback on that. Thank you very much.
Let's take one.
Hope it's a good one. It's the last one. For the narrowband stochastic processes, I'm trying to understand. I understand for narrowband features, you're worried that they'll just keep growing with more integration time. But is that true if they're stochastic? Do they grow faster than the stochastic noise?
If they're stochastic, they have an amplitude. So maybe they, if you integrate more, you can. Well, it depends on the frequency resolution that you have.
Yeah.
If you don't have enough frequency resolution, if you integrate, if you measure for a longer time, then you can, if you change the duration of the stretch, you reduce the resolution, and so you can. So in any case, it is like integrating for longer.
I guess my point is, if they're stochastic, doesn't the PSD or ASD find their level, right? If it's when you have a coherent source, it keeps growing.
Yes.
Longer. So
yes.
if they're stochastic,
yes.
Once you
yes, but for instance, for instance, is that.
Yeah.
See, no, sorry. For instance, if the I mean, you see that the amplitude cannot be. These are all. Oh, sorry. In the simulation, these effects are all of the same amplitude 10 to the 5. So you cannot detect the exact amplitude if the process is narrower than the resolution that you have at that frequency. Yeah, measuring for longer would help in any case.
Thank you.
Thank you.
All right, let's thank our last speaker.